So I'm Antti Moilanen from Professor Päivi Törmäs group from Aalto University, and I will take you out from the topic of superconductivity for a moment and talk about something a little bit different. And I will first say a few words about plasmonic lattices, because after discussing with people here, I learned that many of you are not familiar with the field of plasmonics, so I will just take a few moments to introduce you this system. And then I will present you our recent results done in our group. So we demonstrated a Bose-Einstein condensation of plasmonic quasi-particles. So first of all, the nanoplasmonics, it is the study of the interaction between light and matter at the nanoscale. And we are working with plasmonic nanoparticles, and these small nanoparticles act as antenna for the light, so they can enhance some of the wavelengths, or they can absorb some of the wavelengths. And if we take, for example, this kind of metallic nanoparticle and put it under an optical field, and the size of the nanoparticle is smaller than the wavelength of this optical field, it will actually cause the electron cloud to oscillate, and with some suitable frequency the electron cloud oscillates resonantly with the optical field. And this is called the Plasmon Resonance. And perhaps one of the oldest applications of Plasmon resonances are found from the colors of the stained glass in the old cathedrals, where the production of the colors in this glass is based on mixing small metal nanoparticles into the glass. So different size and shape and material of particles will give you different wavelengths which the nanoparticles absorb or enhance resonantly. And what we do in our group, we take a bunch of these nanoparticles, or actually we produce them with EBL, and we arrange them in a periodic array. And why do we do this? We do this because by setting the lattice periodicity to be on the same order than the wavelength of the optical field, we can enhance the resonances, because these dipoles basically they radiate to each other, and this will enhance the radiation a lot. So we end up having hybrid modes, kind of quasi-particles, which are the combination of the diffracted light in the array and those single particle resonances in each nanoparticle. So they are essentially light photons, but they are coupled to the electron movement in the metal, so they are plasmonic particles. And here are some typical extinction spectrum of our samples. So for example, in the incident perpendicular excitation or optical field, you would expect to see the single particle resonance here higher in the energy as quite widespread resonance, whereas the surface lattice modes would show up as this kind of very sharp funnel-like resonances with narrow line widths, and the Q factors of these modes is on the order of 300. And when we solve the whole bunch of incident angles, we reveal the dispersion relation of our modes. And the nice thing with this dispersion relation and this system is that you can tune this dispersion relation, and you can plan it not only by changing the particle material size and the shape, but only changing the lattice periodicity will shift your gamma point up and down. And this is basically the key in the next experiments that I will show you, the freedom to choose where is your band, dispersion band bottom. And the modes don't live very long, obviously, because we are working at room temperature and there's a lot of metal involved in the system. So they live about hundreds of femtoseconds. And they show some inherent spatial coherence, which is on the order of tens of micrometers without any tricks. And what tricks we can do to compensate for the losses? We add a gain medium on top of this nanoparticle array. In our case, we use fluorescent molecules such as rhodamine or some other dye molecule, and these molecules can then emit photons and absorb photons from the lattice modes, exciting them. And some interesting phenomena that we have been studying with these plasmonic lattices in the past is, for example, lasing phenomena, which means that the fluorescent molecules can start to emit coherently into a single mode in the lattice. So they act like a small nano laser. And this laser light can have extremely narrow line width. So for example, in this work, the line width of the laser light that is coming out from the lattice was 0.2 nanometers. And when it goes into this lasing mode, it also increases the spatial coherence up to 100 of micrometers, which was in this case actually limited only by the physical size of the nanoparticle array. So that's the short introduction to plasmonic lattices. So they are a quite nice system which allow you to study some quantum coherent phenomena at high temperatures. And one interesting point is that because of the photons are coupled to the electron, these quasi-particles possess a finite but very small effective mass. And this gave the original ideas about maybe it is possible to make these guys to form a Bose-Einstein condensate. So this brings me to the main topic of the talk, which is the observation of Bose-Einstein condensation in such system at room temperature. So just as a quick background about condensates, different kind of condensates has been studied extensively during the past century, starting from the helium superfluids, expanding into ultra-cold gases, magnons, inorganic and organic polaritons, as well as pure photons. In 2010, a photon condensate at room temperature was published. And of course, these condensates, like photons and organic and inorganic polariton condensates, are non-equilibrium condensates. So they are not the same thing than condensates made with ultra-cold atoms. And then, of course, superconductivity can be understood as the condensation of Cooper pairs. And we introduced a new family into this member because the particle is not pure photon, it's not polariton, but it's a plasmonic quasi-particle. So let's take a little bit closer look at our experiment. So this is a schematic of the sample. So we have an array of gold nanoparticles. And we put the fluorescent molecules on top of the array, and they are in a liquid solution. And we basically pump the molecules, we excite the molecules at one end of the array using a pulsed femtosecond laser, because this will allow us to excite the molecules but not bleach them. And while we pump the molecules from one end of the array, bringing the photons into the close vicinity of the lattice, being able to excite the lattice modes, we detect what happens on the other part of the array. And this is the dispersion relation of our lattice modes. So you see that the upper dispersion branch has a nice band bottom, and this will be the place where we condensate the quasi-particles. There's also a lower band existing, but there's a quite nice band gap between those. So this will be helpful for us in order to have some kind of trap for the quasi-particles. And then the fluorescent molecules that we are using, they have their characteristic emission and absorption profiles. And one interesting point that I want to point out from this spectrum is a point where the absorption probability of these molecules goes close to 0. And in this beyond this region, the molecules basically only can emit. They cannot anymore absorb photons. So next I will show you a few experiments where we play with the relative distance of this point where the absorption goes to 0 and this band edge position. So, but before that, a few words about the thermalization mechanics. So what is providing the thermalization in the system? It is exactly the emission and absorption cycle with the molecules. So here we have again a schematic of the array, and it's covered with ground state molecules. So this is the molecules are essentially two-level systems which have both electronic states broadened by vibrational and rotational states of the molecules, because they are physically quite big molecules. So they act like springs. They lose their energy into their internal vibrations. So that's why it's not a pure two-level system, but it's a broadened level two-level system. And now as we pump the molecules at one end of the array, it causes some of them to go into the excited state. And these guys will emit photons which will excite the lattice modes, and the modes start to propagate along the array to this direction. And as the modes propagate, they only meet ground state molecules which are able to absorb the photons and emit them back to the array. But as I said, in each cycle of the emission and absorption, the molecules lose some energy. So basically what you should expect to see less and less energetic photons the further away you go from the pump spot, because this is the only place where we bring new high energy excited molecules into the system. So you should be seeing some kind of redshift along the array. And this is what we measure in the experiment. So here's yet again another schematic of our system where the pump is here and the nanoparticle array is here. So in the y-axis we have now the physical distance from the pump spot, and in the x-axis we have the energy or the wavelength of the light coming out from the array. And indeed we see, starting from the beginning of the array, we see that the energy is decreasing. We see the redshift here. But in this case we have chosen the periodicity so that the band edge is higher in energy than the absorption edge. So you can imagine that when the emitted light or the redshifted light, it reaches this point of the band edge bottom, there's still quite high absorption probability from the molecules. So the molecules will absorb the photons and it will emit them to lower energy, somewhere to the lower dispersion branch. And this is because we are so high with our band edge. And this same dynamics can be seen if I integrate over the band edge energy starting from the beginning of the array. This is the blue line. So you see that some stuff gathers into the band edge, but it actually flows away from there. And it actually, the only place where the redshift stops is the place where the absorption is finished, which makes sense because this will stop your absorption and emission cycle. So what happens then if we tune the lattice periodicity so that the band edge resides lower in energy than the absorption edge? So this solid line is always the place where the absorption finishes. In this case, we observe lasing, the same thing that we have been seeing in our previous experiments. So already starting from the beginning of the array, only one wavelength shows emission, and it's very narrow peak. And you can see from the dynamics of the band edge, which is the blue line, and other parts of the spectrum, that indeed starting from the beginning of the array, all of your population is in this single mode, the band edge. And this was done only by changing the lattice periodicity a little bit. The dynamics changed completely. And then you might already guess where I'm going here. When we tune this band edge to be exactly on the same point than the position where the absorption ends, what happens is now we again see the redshift, but as we reach the band edge, the absorption has now finished. So the molecules stop to absorb. And this is a sweet spot where everything else that we pump into the system will go into the ground state. But think about it for a moment. Where did the emission end up into this band edge? It came through this thermalization process. So we didn't start to emit into the band edge from the beginning of the array, but the stuff gathers into the band edge only later after going through the thermalization. And this is the case where we observe the Bose-Einstein condensation. It's actually in this region where the redshift has somehow stabilized. And you can see it from the dynamics also that the band edge really gathers the population until at some point, somewhere here, it actually exceeds the population elsewhere in the spectrum. And what we needed to do to convince the reviewers that we are seeing a Bose-Einstein condensate, first of all, the dynamics, that how did the population end up into this band edge, and the thermalization process that they go through. This is the same mechanism that has been shown in photon and polariton condensates. And but then some other things, taking a closer look at how the population is distributed in this region where we observe the condensate, we can fit a Bose-Einstein distribution function into the population, and it gives us roughly the room temperature, which is expected also based on the simulations of the system. And it also shows nonlinear pump dependency. So at some point, when you exceed the critical photon density, the bosonic enhancement causes the population to go into the ground state, and this is a nonlinear increase in the intensity. And then interesting point here is that the simulations are done in time domain, whereas the experiments are purely done in the space. And the simulation showed already a few years ago that if this is possible in our system, everything should happen in a picosecond. So how it's possible to measure something which happens in picosecond? And this is where this invention of measuring the spatial propagation of the modes came into play, because this revealed basically our time dynamics of the system. And all this mapping between the space and time makes sense if you think about the dispersion relation, because the group velocity of the modes is constant in this linear part of the dispersion. So here every point in the space maps directly into some time if you just calculate it based on how fast the modes propagate along the array. And then we wanted to make sure that the emission that we are seeing from the sample is coming from the dispersion branches, and it's indeed what happens. So we measured k-space images from the beginning and end of the array in the condensate case, and in the beginning of the array you see that one of the dispersion branches is visible, and in the end part we have condensated into the band bottom. And it's indeed only one arm, because we are propagating only into one direction, so only positive k branch is visible. And then we investigated the spatial coherence of the condensate, because it's expected to increase both temporal and spatial coherence. Temporal coherence increase is seen in the Linewidth narrowing, and spatial coherence increase we measured with Michelson interferometer setup, which showed us that the coherence length has roughly doubled from what it was originally for the modes. And then we also did an independent measurement of the spatial coherence by a standard double slit, and it also showed that the coherence of the modes, which we estimated to be in the beginning about 40 micrometers, has more than doubled when we enter this condensate mode. And then about the time dynamics, we already reasoned all these time scales from the simulations and the group velocity of the modes, but we needed to have some hardcore proof of this, so we made a pump probe experiment of our condensate and confirmed that indeed the decay occurs in less than a picosecond. So like this, I want to thank you for your attention and welcome questions.
My general question is whether it's possible to substitute those particles by viscous particles, in this case